All right, let's dive into some physics.
Sounds good to me.
You ready for this?
Oh, yeah, always.
Okay, so you've sent in some materials all about oscillations,
Okay.
specifically focusing on the velocity and position of a horizontal spring mass system.
Right?
We're talking excerpts from an educational website aimed at like a junior college level.
Cool.
And the best part is it's an open educational resource, meaning it's designed for everyone to access and learn from.
That's awesome.
Yeah.
It's really great to see resources like this becoming more widely available, breaking down those barriers to education.
Mm.
And this topic, oscillations, it's more relevant than you might think.
Oh, yeah.
We encounter oscillations every single day, from the swaying of a pendulum to the vibrations of our phones.
Exactly. It's physics in action all around us.
Yeah.
And speaking of action, this source includes a link to a really cool interactive applet
Oh, nice.
where you can actually play with the spring mass system.
I love it.
We'll be sure to share the URL in the show notes. So fire up that applet and get ready to experiment alongside us.
I definitely recommend checking out that applet. It's one thing to hear about these concepts, but seeing them in action,
Oh, yeah.
tweaking the variables yourself, that's where the real aha moments happen.
For sure, for sure. Okay, so while you're bringing up that applet, let's start unpacking the first equation for velocity that the source provides. It's
Right.
derived from the position equation.
Right.
And it looks like this. V equals xo coso.
Okay.
So can you break this down for us a little bit? What are we looking at?
Sure, yeah, let's decode that. So V stands for velocity,
Okay.
which tells us how fast the mass on the spring is moving and in what direction at a particular time.
Okay.
X here is the maximum displacement of the mass from its resting point. Basically, how far the spring is stretched or compressed at its extreme.
Gotcha.
O, omega, represents the angular frequency,
Okay.
a measure of how quickly the system oscillates back and forth.
Mm-hmm.
And T is, of course, time.
Time, of course, yes.
Okay.
So this equation is really helping us understand how the velocity of the mass is changing over time as it like bounces back and forth.
Precisely. Now, one interesting thing to note here is the relationship between the maximum velocity,
Okay.
denoted as v,
Mm-hmm.
and the other variables. We can actually express it as v equals x0.
Okay, so the maximum velocity is directly proportional to the maximum displacement and the angular frequency.
Yeah.
What's so fascinating about that?
What's fascinating is that this simple equation hints at a really fundamental concept in physics, the conservation of energy. Imagine, pulling that mass on the spring further back, giving it a larger x.
Yeah.
You're putting more energy into the system. This stored energy is called potential energy.
Right.
Now, release the mass, and that potential energy transforms into kinetic energy, the energy of motion.
So a bigger stretch means more potential energy, which translates to a higher maximum velocity as that potential energy converts to kinetic energy.
It's like pulling a slingshot further back.
Exactly.
You get a much faster projectile.
That's a great way to think about it. And the angular frequency also plays a role. It's like a measure of how fast the energy is being transferred back and forth between potential and kinetic.
Okay.
Higher frequency means a faster transfer, which can lead to a higher maximum velocity.
Wow, that makes so much sense. It's not just about the equations, it's about the story that those equations are telling us about the
Yeah.
energy dance within the system.
Exactly. You got it. Welcome back
We're back.
to our deep dive into the physics of oscillations. You've heard the equations.
Yeah.
Now it's time to see them in action.
All right.
Have you had a chance to experiment with that interactive applet yet?
I have, and it's amazing
Cool.
to watch the graphs change in real time as you tweak the mass or the spring constant. It really brings those formulas to life. Oh, it's a powerful tool
Yeah,
for visualizing these concepts.
for sure.
And speaking of visualizations, let's unpack that second velocity equation.
Okay.
V equals plus or minus omega, square root of x squared minus x squared.
Yeah.
Remember, this one relates the mass's velocity to its position
Okay.
rather than time.
Okay, so instead of seeing how velocity changes over time, this equation is telling us how fast the mass is moving based on where it is on the spring.
Exactly. It highlights the continuous interplay between potential and kinetic energy as the mass oscillates.
Okay.
Think about it. When the mass is at its maximum displacement,
Mm-hmm.
x equals x0,
Uh-huh.
the velocity 0.
Mm-hmm.
At that point, all the energy is stored as potential energy
Okay.
in the stretched or compressed spring.
Just like that moment at the peak of a swing, right?
Yeah.
You're momentarily still high above the ground,
Yeah.
but you can feel all that stored energy ready to be unleashed.
Perfect analogy.
Yeah.
Then, As the mass starts moving toward the equilibrium point,
Okay. X equals 0. That potential energy is converted into kinetic energy. Right. The mass gains speed, reaching its maximum velocity, v, as it zips through the equilibrium point. At that instant, all the energy is kinetic, pure motion.
so the further the mass is from the equilibrium point, the slower it's moving. And the closer it gets, the faster it goes. It's like the spring is saying, like, come back to the center.
Right.
With a force that gets, like, stronger the further away the mass is.
That's a great way to think about it. The spring exerts a restoring force that always tries to pull the mass back towards equilibrium. And as the mass passes through the equilibrium point and heads towards the other extreme, the process reverses.
Right.
Kinetic energy converts back into potential energy.
Okay.
The mass slows down, eventually reaching zero velocity at the opposite maximum displacement.
So this is starting to paint a much clearer picture
Good.
of the energy dance happening within the system.
Yeah. But wait, we've been talking about a perfect world, haven't we?
Yeah, in an ideal system, the mass would oscillate forever.
Right.
But in reality, we have to account for things like friction.
Right.
That's probably what SHM09 in your source material refers to.
Oh, okay.
A simulation model.
Okay.
That takes some of these real-world factors into account.
So friction, that force that always seems to be working against us,
Yeah.
how does it affect the oscillations of the spring mass system?
Well, friction acts as a kind of energy thief,
Okay.
gradually stealing mechanical energy from the system and converting it into heat. This leads to what we call damped oscillations.
Okay.
Instead of bouncing back and forth forever, the mass eventually comes to rest at the equilibrium point.
So instead of those like perfect symmetrical oscillations we see in the applet, the real world system would have oscillations that get like smaller and smaller over time.
Exactly. Think of a pendulum slowly coming to a halt,
Right.
or a guitar string gradually losing its vibration.
Yeah.
The oscillations decay, their amplitude decreasing, until the motion eventually stops.
So now I'm curious, how do we factor this friction
Right.
into those elegant equations we've been discussing?
Yeah.
Do they need a complete overhaul?
That's a great question. And it takes us into the realm of more advanced models.
Okay.
To account for damping, we introduce a new term representing the damping force,
Okay.
which is typically proportional to the velocity of the mass and acts in the opposite direction of motion.
So the faster the mass is moving, the stronger the damping force trying to slow it down.
Exactly.
It's like a resistance that gets like fiercer the more the system tries to like resist it.
Precisely.
Wow.
And incorporating this damping force makes the equations for velocity and position more complex,
Okay.
involving exponential terms that describe the decay of the oscillations over time.
Okay, that sounds like a whole other level of physics exploration.
It is.
But for now, I think we've covered a lot of ground.
Yeah.
With the basics. So what are the key takeaways you want our listeners to walk away with from this deep dive so far?
I think the most important thing is to appreciate the elegance
Yeah.
and power of simple models, like the spring mass system. We've seen how these models can help us understand complex concepts, like energy conservation and the interplay between forces and motion. And even though real-world systems are always more intricate, these fundamental principles still apply.
It's like having a foundational understanding that we can build upon as we explore even more complex phenomena.
Exactly.
And speaking of exploration, we have one last thought-provoking question for you to ponder as we wrap up this deep dive in part 3.
I do too.
All right, welcome back to the final part of our deep dive.
Back for more.
We've explored the equations, we've visualized that energy dance, and we've even ventured into the messy world of friction.
Right.
Are you ready for one last mind-bending challenge?
Always. Bring it on. Especially when it comes to, like, pushing the boundaries of our understanding.
So we've spent a good amount of time with our single spring and mass, but you hinted that there's a whole other level of complexity that we could explore. What happens when we take this model and, like, apply it to a more chaotic system?
Oh, that's a good question. So imagine instead of just one spring and mass, we have a whole interconnected network of them.
Okay.
Picture, like, a web of springs and masses all bouncing and swaying, influencing each other's movements.
Whoa, that sounds incredibly intricate, like a giant tangled mobile with springs and bobs going every which way.
Exactly. We call these systems coupled oscillators.
Okay.
And they pop up everywhere in nature and technology. Think about, like, the atoms in a solid
Okay.
vibrating and interacting with their neighbors, or the way different parts of a bridge respond to the wind or traffic.
So it's like our spring mass system on steroids.
Yeah.
Instead of one simple oscillation, we've got a whole network of them happening simultaneously, all affecting each other.
Huh.
Oh, my brain is starting to hurt just thinking about it.
Well, it's definitely a step up in complexity.
Yeah.
But the beauty is that the fundamental principles that we've discussed still apply.
Okay.
We're just expanding our scope to include multiple interconnected oscillators.
So instead of those single equations for velocity and position, we'd have like a whole system of equations, each one representing a different oscillator in the network.
Precisely. And those equations would be linked together, reflecting the interactions between the oscillators. It gets mathematically intense, but the core concepts of energy transfer, restoring forces, and damping still hold true.
So even in these like incredibly complex systems, those basic principles we've uncovered can still help us understand the overall behavior. That's pretty amazing.
It is. And what's even more fascinating is that these coupled oscillators can exhibit some truly mind-boggling phenomena.
Oh, like what?
For instance, you might see synchronization,
Okay.
where multiple oscillators, even if they start out differently, end up moving in unison.
So like a group of fireflies all blinking in sync.
Yeah,
Or a choir hitting that perfect harmony.
exactly. And there's also resonance, where a small input can lead to dramatically amplified oscillations. Think of a singer shattering a glass with their voice.
Oh, wow.
That's resonance in action.
Okay, you've officially blown my mind. I need to sit down and process all this. But I can see how, like, understanding coupled oscillators could open up a whole new way of looking at the world.
And that's what we hope we've achieved with this deep dive.
Yeah.
Giving you a foundation to build on, sparked your curiosity, and equipped you with the tools to explore further.
Yeah.
The world is full of oscillations,
It really is.
from the subatomic to the cosmic, and there's always more to learn and discover.
Couldn't have said it better myself. So to our listener, we encourage you to keep that interactive applet open. Play with the variables. See what other insights you can uncover. And maybe, just maybe, you'll start to see those coupled oscillators everywhere you look.
The universe is a symphony of motion, waiting for us to decode its intricate rhythms.
Thanks for joining us on this incredible journey through the world of oscillations. Until next time, keep those brains buzzing and never stop exploring.